Hello everyone, I am Najma Nazari from the University of California, Davis. I am a member of ASIC Research Lab with the supervision of Dr. Human Homayun. This course development curriculum is funded by Intel Corporation. In this talk, we will talk about implementation of AES in FPGA hardware. This is the fifth video, part B, in a series of training modules that would explain how to design hardware accelerator using DPC++ on Intel Dev Cloud. This is the outline of our talk. First, I present the goal of these slides, and then we will review AES. After that, I present RTL design methodology, and then I talk about how to implement AES in hardware using RTL design. The goal of our talk is to eventually develop the RTL code of AES. Based on the RTL design methodology, you will learn how to design data path and controller of digital system. Finally, we provide the basic material that you will need for RTL implementation of AES. In the second video, we talk about AES. This slide shows an overview on AES. AES is a popular cipher, a method or process used to change raw information called encryption, and it uses a known external piece of information key to uniquely change the data. It is reversible. It means it can be applied again to put the information back into its original form, called decryption. AES includes 3 block ciphers: AES-128, it is confidential; AES-192, it is secret; and AES-256, it is top secret. In fact, the most secure one is AES-256, and AES-128 is the fastest one. The block size in AES, for example, if it is 128 bits, it means 16 bytes. And each cipher encrypts and decrypts data in blocks of 128. This slide shows the AES-128 schematic. AES operates on 128-bit block, which is 16 bytes as a grid of 4x4 matrix. Each cell in the matrix contains a 1 byte. We XOR the block with the first round key and then apply the certain function that includes substitution and permutation. Then XOR with the next round key and do this process again. We do 10 times for 128 AES. Note that in the last round, mix column step is actually missing, and finally we XOR with the last round key and out comes the output. Always output keep 4x4 arrays. 16 bytes. For more information, you can check the second video. Let's first look at the structure of typical digital system. As you can see, a digital hardware usually consists of 2 units: a data path, which is the execution unit, and a controller, which is the control unit. Input data goes to data path, and the output data will be generated by data path. All control and status input must go to the control unit, and this unit can output those signals. 2 control and execution units communicate with each other through the control and status signal. Data path or execution unit sends a status of itself to the control unit, and controller sends control signal to the data path to control the execution of system. From this structure, we can infer how to develop the RTL. A hardware design is given by its interface and its functionality. The interface can be given as a table of inputs and outputs and their corresponding width. The functionality of system can be given as pseudocode. When we have this information, we can infer the data path and controller. To design the data path, we can first draw the block diagram and then write the HDL code for it. To design the controller, we can draw the ASM chart and then convert it to the HDL code. In the next slide, we talk more in detail about the step of RTL design. To do RTL design, first we must have the interface, pseudocode, and the description for the system. We should divide the interface to two parts, as some of them are related to data path and others are related to controller. Then, based on the pseudocode and interface, we design the block diagram for data path and ASM chart for the controller. Then we can write the HDL code for each part, and we should have a top-level unit to connect those parts together. We should write test bench for data path, controller, and top-level unit to be able to do functional simulation and debugging. If the simulation passes the test, we can synthesize this design and then implement it to perform the static timing analysis. Eventually, we can port the design to FPGA board and test it. Let's look at an exercise. Assume that we want to design a hardware to calculate the average of k numbers and keep the three largest value in three variables called number 1, number 2, and number 3. The pseudo code is as follows. We have three variables for those three largest values, and then we have another variable called sum to keep the sum of inputs. In a for loop, we read the input and add it to the sum variable to keep the sum of all inputs. Then we check if the input is bigger than the current largest saved value or not. If it is bigger than any one, we keep it and change the order respectively. At the end, to calculate the average, we divide the sum by number k. This is the interface of design. For any digital design, we need a clock, reset. We may need another signal to tell us if the input is ready, such as go, and we can have a signal in the output to show that our execution are done. In this example, we have the out underline mode signal that tells the system to output the desired value. In the next slide, we discuss it in detail. As you can see, this is the interface table. The out underline mode determines what we should show on the output. If it is 0, we must show average value on the dia out. If it is 1, then we must show number 1, and so on. Now we have the pseudocode and interface table, so we can design the block diagram of data path. To draw the block diagram, we should look at the pseudocode to determine what function we need. For example, we need an adder to add the inputs. We need comparator to compare the input with current saved values. We need a divider to calculate the average. As you know, dividing can be done by shifting in digital systems. We need a multiplexer at the output to help us to output the correct value based on the dout underline mode. We need 3 registers for saving the 3 largest value. Also, we need another register to keep the track of number k for loop iteration. Now, we can connect these units together and determine the control and status signal that we need for the controller unit. The top level should look like this. As you can see, we divided the interface into data path and controller. We can find the critical path of a design as follows. Calculate the delay of all passes that start from an output of a register and go to the input of a register. A path that has maximum delay is the critical path. If we have critical path delay, then we can calculate the minimum clock time of a design, and it should be equal or bigger than the delay of a register plus delay of a critical path plus setup time of a register. Setup time is the amount of time the data at the synchronous input must be stable before the next active edge of clock. Hold time is the amount of time the data at the synchronous input must be stable after the last active edge of clock. Now, let's see how we can design the AES-M chart. Any AES-M charts have 3 main elements: a state box, a decision box, and a conditional output box. A state box is used in more type machine and shows the output signal or the action. Conditional output box is used in melee machine and it shows the conditional output or an action. We can divide the AES-M chart to multiple AES-M blocks. Each AES-M block contains 1 state box, 1 or more decision box, and 1 or more conditional output box. However, having decision box and melee output is optional. There are some rules in AES-M chart. First, transitions are governed by clock, and transitions only occur between AES-M blocks. For each input, there is only 1 path to the output, and you cannot have a closed loop in AES-M chart unless it includes a state box. Look at this example, which is a finite state machine. We have 3 states. The initial state is A. As reset goes to it, with each input, we can change the state and the output changes only if the current state changes. For the state machine, we can draw this AES-M chart. Now, let's draw the AES-M chart for our exercise. We can see the AES-M chart for the exercise in the left figure. The right figure is the simplest version that in each conditional box, we only write the name signal that we want to set 1. In this exercise, we wait at the S_waiting state after reset until we receive the go signal. Then, we go to an state that we can add the input and calculate the sum of all inputs. In this state, we also can check that if the input is bigger than current saved values or not. If it is, then we can perform the appropriate action in the conditional boxes. For example, change the saved value order and replace the smaller value with the current input. Then we can check weather index for loop operation to see if we are done or not. As you can see, to calculate the average, the division happens in the data bus automatically by shift operation, and we do not need to take care of it in the controller. Also, the out underline mode directly selects the corresponding output, and we do not need to set or check it here. Now it is the time to design AES based on RTL design methodology. First, we check the pseudocode. Then we design the data path and controller. This is pseudocode for AES. First, let's determine what would be the input and output. We get input data that needs to be encrypted, the key, and some control signal to start the encryption. We must generate the encrypted output, and you already know how AES works. As we can see, we need subbyte, shift row, mix column, and add round key in our data path. This is the interface of AES. We are now going to describe how this module must work. After the reset, the module waits until it gets the init signal. When the AES is ready to get inputs and is in idle mode, AES must set ready signal 1. When the user sets init signal, AES starts to generate the key for each round and save them in a memory. In this way, we do not need to generate key for each round. When the initialization is done, we set the done underline init signal 1. After that, when the DIN is ready by the user must set the start signal to 1. In this case, AES starts to encrypt the input, and when all the round is done, module must set the down signal to 1, and the out will show the encrypted message. This slide shows how you should divide the interface for the data path and controller. This diagram shows the internal of AES data path. Key update module is for the initial phase of AES that generates the key for each round and save them in the RAM. RAM module is the encryption core, which contains all sub-functions related to the encryption for each round. We can see the input signals and output signals too. Inside the RAM module, we have subbyte, shift row, and mix columns. We can see how the key for each round comes to this module and will get to use after mix columns. How to implement each sub-function is your responsibility to design them based on their pseudocode. Now, let's look at the inside of key update module, which is responsible to generate key for each round. As you can see, the internal structure and easily can be written by HDL. For archon values, we save them in the RAM and use those values. And eventually, this is the ASM chart for the control unit. When the reset comes, we set the round to 0. Then we go to state ready where AES module can receive input. If the init signal is set, we go to initialize the keys. We generate the keys for all 10 rounds, and then we set down underline init signal. Then we back to ready state. Now we should wait till receive a start signal. When it comes, we can perform the encryption, and when the process is finished, we can set the down signal to 1. Thank you for watching. I encourage you to follow up with other videos, and there will be also a GitHub repository that provides all the code.